recording now. So this section is over gases. So some properties of gases are that they have indefinite shape, meaning they will take the shape of whatever container you put them in. They have indefinite volume, meaning they expand to fill whatever container they're put in. They can be compressed. So when we talk about a state of matter being compressible, we mean we can squish the particles together and they'll still be in the same state. So gases are compressible. Liquids and solids are not compressible. If we try to squish liquids, we're going to squish them and they're going to be a solid. So they change states. When we talk about gas pressure, we're talking about the gas particles pushing or exerting a force on the container they're in, their surroundings. When we talk about matter, we are describing the kinetic theory of matter. And so the basis of the kinetic theory of matter is that all particles that make up matter are constantly moving. And then when we apply kinetic theory specifically to gases, because of the properties of gases, there are some assumptions. And one of those is that the gas particles are so small compared to the container that they're in that their volume is zero or negligible. The gas particles are constantly moving. If they collide with each other, they collide and bounce off with the same energy they started with. So if the particles do happen to collide, they're not going to exchange energy. There are no attractive or repulsive forces between gas particles because they're so far apart. That is how we define a gas, and the typical properties of a gas is that the particles are not interacting with each other. So they're not held in a rigid structure, and they're not held at a given volume. They can move around and expand to fill their container. And we describe their average kinetic energy as their temperature in Kelvin. So when we're dealing with gases, the temperature has to be in Kelvin. So just as a reminder, if you're converting from Celsius to Kelvin, you take the temperature in Celsius and add 273. The reason why we use the Kelvin scale is because it doesn't have negative temperatures. So if we're using temperature in place of kinetic energy, how much the particles are moving, we wouldn't want negative values for that. That wouldn't be a negative value wouldn't be a good representation of particles moving. And so the Kelvin scale, the theoretical lowest temperature is 0 Kelvin, and that would be the temperature at which we theoretically had matter where the particles weren't moving. So we would have particles, we'd have a substance that has mass, but not volume. And this I did move around, so I'm here, but when we talk about gases, and all the gas laws we're going to talk about in this section, we're treating the gases as if they're ideal gases, meaning that they are at very high temperatures and low pressures, so much that the gas particles don't have any volume relative to their container, and there aren't attractive forces between the particles. If we have a gas that's at a low temperature and high pressure, then we describe it as a real gas. And so our description of gases in those situations is different. And if you go on to take thermodynamics in college, then you'll talk about how to handle real gases. But for our intents and purposes, we're going to treat gases like they're ideal. Then we talked about Avogadro's hypothesis. So Avogadro, our favorite chemistry person, said that if we have an ideal gas, two ideal gases at the same temperature and pressure, those two gases will have the same volume for the same number of particles. And so that's going to allow us to describe the molar volume of a gas at STP. So I think we left off here last class talking about standard temperature and pressure. So standard temperature is defined as 0 degrees Celsius or 273 Kelvin, and standard pressure is 100 kilopascals. And so based on Avogadro's hypothesis, scientists developed another conversion factor for us, and that is molar volume of a gas at STP, or standard temperature and pressure. So any ideal gas at 0 degrees Celsius and 100 kilopascals, 1 mole of that gas will occupy a volume of 22.7 decimeters cubed. And we worked the first 2 examples, is that right? Okay, so now let's work the third example. I don't think you guys did that one. So this one, you're actually going to have to write out the reaction and use this new conversion factor. So I'm going to give you guys a few minutes to get the reaction down and make a plan, and then we'll work it out together. So we start out with sodium nitrate. What's the formula for sodium nitrate? NO3 solid. And it decomposes into sodium nitrite, which is and oxygen. Maybe for the state. So then we need to balance the reaction. What did you guys do to balance it? 2, 2, 1. Good. And we're told that we want to calculate the volume of oxygen gas in meters cubed produced when 3.100 grams of sodium nitrate decomposes at STP. This reaction is happening at STP. So since we have a gas at STP, that allows us, if we need to use that new conversion factor. So this is a stoichiometry problem, right? We're going from amount of sodium nitrate into amount of oxygen. The difference is we have a new conversion factor that we're going to use. So we're going to start out with what we're given, 0.00 of nitrate. We're going to go grams of sodium nitrate and moles of sodium nitrate. I'm going to grab my calculator. Did you guys get 85 for the molar mass? 0. So that cancels out grams of sodium nitrate. And we're going to go moles of sodium nitrate into moles of oxygen. And the mole ratio there. 1 to 2. And then this is where you're going to have to, what you're going to find is you've done so many stoichiometry problems that you are probably at muscle memory for now putting in molar mass, right? You are at the point where that's what you do. You don't even have to think about it. But I'm looking not for grams of oxygen, but for volume of oxygen. So am I going to need molar mass? No. Because of my gas is at STP, I can use that conversion 0.7 decimeters cubed. But that I can only use if it's a gas, right? It's in a gas. And is it STP? Okay, then I can use it. So occupy volume of 2.7 deciliters cubed. Okay, well, I have volume, right? But what I asked to find volume in? Centimeter cubed. So, how am I going to do that? You fail the test. Okay, so let's talk through this nice and slowly. Do we know a conversion factor between centimeters and decimeters? What is it?
I think it's 10, or 1 decimeter.
So I'm going to use this, but I need decimeters cubed and centimeters cubed. So what can I do to that conversion factor? Cube everything. So cube the 10, cube the centimeter, cube the 1, the decimeters cubed. No, cubed the decimeters, not cube the decimeters cubed. Nope, cubing decimeters cubed would give you decimeters to the 9th. But it wouldn't, the units wouldn't cancel out. You'd end up with centimeters cubed over decimeters to the 6th, which doesn't tell you anything. It tells you did something wrong. Pardon? Yes, because they're just one apart when you look at the metric prefixes. So in 1 deci, there's 10 centi. So 1 deciliter is 10 centiliters. But in this case, we started out with meters and just cubed them. What's 10 cubed? 1,000. Okay, so let's work this out. And what do we get? $413.9 centimeters cubed of oxygen gas. Very good.